Day 47 inside the habitat. The battery state of charge has been dropping 0.2% per hour for the last 6 hours. Not catastrophic. Not yet. The crew knows it. The commander has already begun calculating what can be shut down if the number doesn't stabilize by morning. The lighting in the hab has been dimmed. One of the 2 water recyclers is offline to save power. And in the small hours of the Martian night, everyone is awake, watching a screen, waiting to see if the solar arrays will pull them back to safety at dawn, or if they'll need to make harder choices. This is not an emergency. This is Tuesday on Mars. Mars is not a place where one thing kills you. It's a place where the collapse of margins kills you, slowly, predictably, across weeks. A Mars habitat isn't a base. It's 3 systems locked in a loop: power, atmosphere, and water. Each one feeds the others. Each one can starve the others. If you lose one, the rest lie to you. They keep running for a while, burning reserves, until the numbers betray you and the loop breaks. The mission isn't 500 days of survival. It's 500 days of keeping that loop intact. Power is first, because nothing else runs without it. For a crew of 4, the habitat needs an estimated 15 to 25 kilowatts continuously. For 6 crew, it climbs to an estimated 20 to 40 kilowatts. Not quite linear, because the habitat has a fixed baseline for heating, computing, and life support that doesn't scale with bodies. That's lighting, computers, water pumps, heating elements, the carbon dioxide scrubbers, the oxygen generators, the freezers, the communications array. Tens of kilowatts sound small, until Mars takes half of it away. Mars takes it with dust. Every sol, an estimated 0.1 to 0.3% of solar panel efficiency vanishes under a film of particles smaller than talc. That's the baseline. Then come the regional dust storms. Atmospheric opacity, measured as tau, can jump from 0.5 on a clear day to 3 or higher during a storm, an estimate based on rover data. When tau hits 2, you're getting maybe 20% of normal sunlight. When it hits 3, you're in twilight at noon. The exact impact on power depends on array design, tilt angle, and how often you can clean, all estimates with real uncertainty. The batteries have to cover the gap. For a regional storm lasting 2 weeks, you need somewhere in the low thousands of kilowatt hours of storage, an estimate, and one that depends on how much you're willing to shut down. But here's the trade-off. Oversizing the solar arrays and building a strict load-shedding plan often beats carrying massive battery banks, at least by mass and reliability, an estimate that mission planners argue over. The batteries themselves are lithium-ion, because nothing else gives you the energy density for the mass budget. But lithium-ion doesn't like Mars. The habitat stays warm, but the battery enclosures outside swing between an estimated -70 at night and 20 during the day. You can insulate them. You can heat them. But every what's spent keeping batteries alive is a what not keeping people alive. Some missions skip this problem entirely. A small fission surface power unit could provide tens of kilowatts electric continuously, an estimate, day and night, dust or no dust. It's heavier at launch, more complex to certify, and politically harder to approve. But it doesn't care about tau. The mission we're watching chose solar. That choice has consequences. By day 30, the issue isn't survival, it's whether their margins are growing or shrinking. The crew runs a cleaning pass on the solar arrays every 3 days. It's done with a small robotic arm and soft brushes. No water, because water is mass they can't spare and ice that could crack the panels. Each cleaning recovers an estimated 2 to 4% efficiency. But the arm has bearings. The bearings have lubricant. The lubricant degrades in vacuum and cold. There are 6 spare lubricant cartridges. Once they're gone, the arm runs dry and cleaning stops. Then dust wins. If dust cuts solar, they don't adapt. They choose what dies first. The hierarchy is written into the mission rules, but it still has to be decided by humans in real time. First to go, non-essential computing. Personal devices, entertainment systems, anything streaming data back to Earth that isn't critical. Second, one of the 2 water recyclers. Third, the backup oxygen generator. Fourth, heating in the crew quarters. They keep the core warm, the lab, the med bay, the galley. The sleeping pods drop to 10 Celsius. You can survive that in a sleeping bag for a while. Fifth, you start talking about whether the science missions continue or whether you go into minimum power hibernation mode until the storm clears. No one wants to be the crew that came to Mars and spent months in a dark tube waiting for the sun. The scariest failures aren't explosions, they're numbers drifting, pressure, CO2, battery state of charge. Atmosphere is the second system, and it's the one where every number has to stay inside a narrow envelope or people start dying in ways that are hard to notice until it's too late. The habitat is pressurized to an estimated 34 to 55 kilopascals, depending on design, roughly a third to half of Earth's sea level. That's enough to keep water liquid and lungs functional, but low enough to reduce the structural load on the walls and cut the leak rate. The mix is around 30% oxygen, the rest nitrogen, with CO2 held to a few thousand parts per million. Standards vary, but go much higher and cognition starts to suffer. Every person consumes an estimated 0.82 to 0.89 kilograms of oxygen per day, a high-confidence estimate based on metabolic data. That oxygen comes from water electrolysis. You crack water into hydrogen and oxygen, vent or store the hydrogen, breathe the oxygen. It sounds simple. It's not. The electrolyzer runs on power. It has proton exchange membranes that are fragile, prone to fouling, and impossible to manufacture on Mars. The membranes are a likely failure point. So are the pressure sensors, the solenoid valves, and the water feed regulators, all estimates of where the system is most vulnerable. There are 2 electrolyzer units. If one fails, the other can supply a crew of 4, barely. For 6, you're in deficit unless you cut activity levels. No EVAs, no heavy work, everyone on rest shifts. The CO2 scrubbers are worse. They use amine-based sorbent beds that have to be regenerated every cycle by heating them to release the captured carbon dioxide. Each cycle degrades the sorbent slightly. The beds are good for an estimated 500 to 800 cycles before performance drops below safe margins. The mission is 500 days. If a bed fails early, you're running 1 unit at double duty, which means double the regeneration cycles, which means faster degradation. There are 2 spare sorbent canisters. Once those are installed, there's nothing left. And CO2 is invisible. You don't feel it until you're slow, confused, headache building behind your eyes. By then, the number on the sensor has been drifting for hours. Day 93. The backup scrubber throws a fault code. The controller thinks the temperature sensor is out of range. It might be the sensor. It might be the heating element. The crew has 3 spare sensors and 2 spare heating elements. They pull the unit offline, run diagnostics, and find that one of the quick disconnect fittings on the coolant line has a hairline crack. Coolant leaked, the temperature spiked, the sensor reported truth. The fitting gets swapped. But that's 1 fitting gone. There are 11 spares for the entire habitat. Every backup pump buys safety and steals mass from something else they also need. Water is the 3rd system, and it closes the loop. Water is oxygen. Water is hydrogen for fuel cells if you have methane or brought it. Water is cooling for the electronics. Water is drinking, hygiene, food prep. The crew needs an estimated 3.5 to 4 liters per person per day for personal consumption and hygiene under strict rationing. Sponge baths, no showers, every drop counted. But that's only part of the loop. The total water budget must also cover oxygen generation and absorb the losses in every recycling pass. The habitat starts with 8,000 liters in reserve tanks, an assumption based on realistic mission planning. Sounds like plenty. It's not, because water is never just water. It's gray water, black water, condensate, brine. And every recycling pass loses a little. The primary water recycler is a multi-stage beast: filtration, reverse osmosis, catalytic oxidation. It recovers an estimated 93 to 95% of input water. 5 to 7% vanishes, bound up in filters, lost to vapor, locked in brine that can't be processed further. The brine has to be stored. There are only so many tanks. The filters clog. Pre-filters last an estimated 60 days. Fine filters, 90. Reverse osmosis membranes, 180 if you're lucky, all estimates. There are filter cartridges and membranes in the spare's inventory. The mission is 500 days. The math does not add up unless the recycling rate stays near perfect and the crew stays below nominal water use every single day. Day 130. One of the crew gets sick. Mild gastro, probably from stress or a contaminated food pouch. Vomiting, diarrhea. Recovery takes 4 days. But that's 4 days of elevated black water input and higher cleaning loads. The recycler runs an extra 8 cycles that week. One filter cartridge clogs early and has to be swapped. The spare's inventory drops. Day 168 brings a quieter crisis. The calibration gas canister for the oxygen sensor array runs low. The sensors drift over time, temperature, pressure, exposure to humidity, and need to be zeroed against a known reference every 60 days. There are 2 spare canisters of calibration gas. If they run out, the sensors keep working, but the crew has no way to verify accuracy. A slow sensor drift of 0.5% could mean the difference between safe and hypoxic, and no one would know until someone passes out. They ration the calibration cycles, stretching them to 90 days. It buys time. It doesn't solve the problem. A tiny leak isn't scary today. It's scary on day 200, when spares are already burned. The habitat isn't welded steel. It's composite fabric layers, polymer bladders, structural ribs, all rated for an estimated 10 years in the Martian environment, an estimate based on accelerated testing. The seals around hatches, around the airlocks, around pass-throughs for cables and pipes. They're elastomer, and elastomer hardens in UV and vacuum. The habitat loses an estimated 50 to 200 grams of atmosphere per day to minor leaks, acceptable because the oxygen generator can cover it. But if a seal fails hard, if a micrometeorite punctures a layer, if a structural fitting cracks, then you're losing kilograms per hour and the clock is ticking in minutes. The crew has patch kits, fabric patches, polymer sealant, metal shims. They have a small ultrasonic welder for composite repair. And they have a pressure map, sensors embedded in the walls that show differential pressure and help locate leaks. Day 214. The map shows a yellow zone near the airlock. Pressure is down 0.3 kilopascals. Not catastrophic, but it's new. 2 crews spend 6 hours tracing the drop. They find it in a valve seal on the air equalization line. The seal is a small O-ring 30 millimeters across. It's cracked. There are 42 spare O-rings of that size. 41 now. The seal is replaced. Pressure stabilizes. But everyone is thinking the same thing. What happens when the spares run out? The mission-critical items aren't the big modules or the shiny robots. They're the small things. O-rings in a dozen sizes. Filter cartridges for the water loop, pre-filters and fine filters combined. Sorbent beds for the CO2 scrubbers. Lubricant cartridges for the cleaning arm and airlock mechanisms. Spare sensors for pressure, temperature, oxygen, CO2. Quick disconnect fittings that join fluid and gas lines. Pump impellers that move water and coolant. Calibration gas to keep the sensors honest. These 8 categories of parts, small, mundane, irreplaceable, decide whether the mission succeeds or fails. And every one of them has a count. Every swap brings the count closer to 0. The 3 systems aren't separate. They form one loop, break one link, and the others lie. Day 260. The primary water pump fails. It doesn't seize, it just loses flow. The impeller has worn down. The pump still spins, but it can't move enough water to keep the recycler fed. The backup pump comes online automatically, and water flow resumes. But now they're on the last pump. There is one spare impeller. If the backup pump fails before they install it, or if the spare fails, the recycler stops. If the recycler stops, they're on reserve water. At 4 liters per person per day for a crew of 4, 8,000 liters lasts 500 days, barely, if no water is used for oxygen generation. But oxygen generation needs water. So the loop breaks. The commander calls a meeting. The options are, install the spare impeller now, preemptively, and hope it lasts. Or wait until the backup pump shows wear, and risk a gap in water processing. Or reduce water use further, 2 liters per person per day, and accept the health and morale cost. They argue for an hour. One crew member says they should install it now. Another says they should wait and preserve the spare for a worst-case failure. A third says cutting water rations is the safest bet. Buy time, reduce stress on the system. The fourth stays quiet, too tired to engage. They've been awake for 19 hours, covering a maintenance backlog. Fatigue is a failure mode that doesn't show up on schematics. They compromise. Water rations drop to 3 liters per person per day. The spare impeller stays in storage. The backup pump gets monitored every 6 hours. It's not a solution. It's a delay. So what's the weak link? 3 candidates: power and dust, leaks and seals, or pumps and filters. Power is relentless. It degrades every soul, and a bad storm can crater margins for weeks. Leaks are insidious. You don't know which seal will crack next, and once spares are gone, there's no plan B. Pumps and filters are the mechanical heart of water and oxygen, and when they fail, the loop starves fast. If you forced a choice, power is the leading candidate, an estimate, not a guarantee, because everything downstream depends on it, and dust is patient and undefeated. But a habitat that solved power with nuclear could still die from a seal failure or a clogged filter. There is no single throat to protect. There are 3, and they're all narrow. By day 300, the habitat is running on margins so thin that every decision is triage. The solar arrays are running at roughly 3/4 of original capacity. An estimate, dust and degradation compounding. The backup oxygen generator has been offline for roughly 2 months to save power. One of the 2 scrubbers is on its 3rd sorbent bed. The primary water recycler is on the backup pump. Filter cartridges are down to a handful of replacements. Several O-ring sizes are down to single-digit spares. And the crew is tired. Not just physically. Tired of the sameness. Tired of the noise, the fans, the pumps, the hum that never stops. Tired of the smell, because the recycler can't strip every volatile and the hab smells like sweat and plastic and faint mildew. Tired of the lack of privacy, because the sleeping pods are 2 meters by 1.2 and you hear everything. Day 319. 2 crew members have a fight. It's about an EVA. One of them thinks the risk is acceptable. There's a solar panel that needs cleaning and the robotic arm is down. The other thinks it's not worth it, not with weather reports showing a dust front approaching. Voices are raised. It's the first real conflict, and it lasts 10 minutes before the commander steps in. No one throws a punch. No one threatens to quit. But the space feels smaller afterward. Day 350 brings a decision point. A regional dust storm is building, Tau estimated to climb past 2.5. It'll last an estimated 10 to 15 days. The batteries can cover it. If they shut down the backup water recycler, drop hab heating to minimum, cut all non-essential science, and run the scrubbers on minimum cycles. That means CO2 levels will drift higher, still safe, but closer to the edge. It means no showers, no laundry, no hot meals. They do it. For 12 days, the hab is cold and dark and quiet except for the essential systems. The crew stays in sleeping bags most of the time, rationing movement to conserve oxygen. They talk less. They sleep more. Day 361. The storm clears. The batteries are down to roughly 1/5 of capacity, an estimate. The sun comes back. The arrays charge. The numbers creep up. By day 400, they've survived the worst of it. But the question shifts. It's no longer, can we make it? It's, what did we spend to get here? Day 500 isn't just, we made it. It's, what did it cost to keep the loop alive? The crew reaches day 500 with all 4 members alive, the habs still pressurized, the system still running. That's success by the mission definition. But look at the illustrative scenario metrics, estimates, not real mission logs. Power uptime across 500 days, around 9/10, meaning they spent roughly 45 days in some level of load shedding or brownout. Water recycling efficiency, averaged in the low 90% range over the mission, below the design target, meaning they burned reserves faster than planned, an estimate. Oxygen autonomy at day 500, perhaps 12 days of reserve if all generation stopped. A thin margin, but positive. Spares consumption, Around 60% of O-rings, roughly 80% of filter cartridges, all sorbent beds, all lubricant cartridges, one of 2 impellers. The numbers say, survived barely. The solar arrays are running at an estimated 2/3 capacity. The last spare sorbent bed is installed. Filter cartridges are down to a handful. O-rings in critical sizes number in the teens. 1 spare impeller remains. The backup oxygen generator is functional but hasn't been tested in months. The robotic cleaning arm has been offline for weeks. The science return is incomplete. 2 planned EVAs were scrubbed due to power margins. 3 experiments were shut down early to save compute resources. The geology samples are fewer than hoped. The long-duration health data is solid, but it's data bought with stress fractures, literal and metaphorical. Was it worth it? Depends on what you measure. They proved a crew can survive 500 days in a closed-loop habitat on Mars. They identified a dozen failure modes that need redesign before the next mission. They burned through spares faster than models predicted, which means the next habitat needs more mass or better recycling or both. They learned that the psychological load is as real as the engineering load, and that you can't model your way out of humans being human. The case for, they survived. They gathered data. They pushed the boundary of what's possible and came back with knowledge that makes the next mission safer. Around 9/10 power uptime is a success when you're running on solar in dust. Water recovery in the low 90% range, even below target, kept 4 people alive for 500 days. 12 days of oxygen reserve at the end means the system held. The case against, the cost in mass, in risk, in crew health was enormous. The margins were never comfortable. 1 more pump failure, 1 more storm, 1 more seal crack at the wrong time, and the loop breaks. We sent 4 people to the edge of survival and called it progress. A mission running on nuclear power and better redundancy might have kept those margins wide, kept the crew safer, kept the science alive. The middle path, maybe day 500 isn't the end. Maybe it's calibration. Maybe we learn that 500 days is possible but not sustainable, and we redesign for shorter surface stays with more robust supply chains. Or maybe we learn that the loop can be closed tighter, that we can grow the margins, that the first crew bought us the data to make the second crew safer. Maybe success isn't the mission that went perfectly, it's the mission that failed in predictable ways and taught us what to fix. Mars is not waiting for us. It's indifferent. It will take the water from your lungs, the heat from your blood, the power from your batteries, and it will not pause. The only thing holding the loop together is the people inside it, the engineers who built it, and the willingness to accept that survival at the edge is not the same as thriving. Day 500 is not a finish line. It's a data point, a proof, fragile and hard one, that the loop can hold. For now. And the question we carry back is not whether we can go to Mars. It's whether we can go and come back whole. And whether the knowledge we gain is worth the price we pay in the counting of O-rings, and filter cartridges, and sorbent beds, and days spent cold in the dark, waiting for the sun.